In 7.4, we're going to learn how to do arc length and surface area. Let's start with a closed piece of curve, a curve on a closed interval. If we want to find the length of this curve from the beginning to the end, we can't just measure a straight line. So what we need to do is break that curve down into a bunch of smaller pieces. So let's look at this piece and pretend that that's just one of our smaller elements and see what we have here. Now, if we have made this infinitely small, and there's an infinite number of them, then we can actually use the hypotenuse of this right triangle to estimate the arc length. Now, think about it. If you have a curve that is in many different pieces, like this, and you take each of those little pieces and you estimate those hypotenuses as being the curve, you see that when you use the smaller these little elements are, the more accurate your arc length is going to be. So we're just using this one right here as an example to figure out a formula to find the arc length of any closed curve or curve on a closed interval. So we're going to call this f of x, and we're going to say that x starts at A and goes to B. This is for later. What I want us to look at as far as the formula goes is this side right here is the dx. If I was doing vertical elements, this would be dy, okay? On any scale, you have a change in x and a change in y. When you're talking infinitely small, and then an infinite number of them, we can use dx and dy. But just look at this for now. We're going to call the arc length s. Then s is going to be the square root of each of the sides squared and added together, right? So when we think about that, we've got an infinite number. We're going to add them together. That gives me an integral. And I'm going to integrate or sum. I'm going to use dx because we're infinitely small, and dy. Now, an integral isn't any good without the d whatever here. I'm doing this in dx, okay? So if this is dx, then the y is just the change in the y value. It's the rise. Watch this right here. A little bit of a manipulation. I've got dx squared. And watch this. Dy over dx squared times dx squared, all under the radical. Now, I can factor out a dx squared and pull it out of the integral. That's going to give me 1 plus dy over dx squared dx. So now I can integrate with respect to x, and this right here is just the derivative of the function. Very simple, right? So let's get our formula for arc length. So arc length of a curve on a closed interval is the integral from the beginning to the end of 1 plus the derivative squared dx. So for all of these problems, you're going to do a few things. You're going to find the derivative, you're going to square it, you're going to add 1 to it, and then you're going to take the square root of the whole thing, and then you're going to integrate, okay? For example, let's look at the function y equals x cubed over 6 plus 1 over 2x. On the closed interval from 1 to 2. Okay, we don't have to graph this. We can just do the busy work here. So I need to know the derivative first. So that's going to be x squared over 2 minus 1 over 2x squared. All right, now that has to be squared out. We're going to take this step by step. I'm going to factor out a half. It'll make this easier. I also have to square that. Pull out a 2 in the denominator and then square it. That's going to leave me with x squared minus 1 over x squared that I have to square. So it's x to the 4th. The first times the second, that gives me a 1, and I'm going to need to get that twice, so minus 2. And the last times the last will be positive 1 over x to the 4th. So that's y prime squared. Next, I need to add 1 to that. Now, when I distribute that 1/4 to the minus 2, that's going to become a half. Add that to this, it's minus a half, right? So we're going to end up with 1/2 plus x to the 4th over 4 plus 1 over 4x to the 4. That's what we're going to integrate under the radical sign. Well, integrating the square root of this is going to be not so easy, right? But watch this. I'm going to factor out a 1/4, and I'm going to rearrange some things. I'm going to get 1/4 times x to the 4th plus 2 plus 1 over x to the 4th. Does that look familiar? It looks kind of like what I had right here, except for the minus sign. Well, where did this come from? It came from squaring this out. So you see this is a perfect square. Sometimes it happens. So this is 1 over, I'm going to write it this way, 2 squared times x squared plus 1 over x squared. That's what's going to go under the radical. S is the integral from 1 to 2. I'm going to factor out the square root of the 1/2. And on the inside, oops, I forgot my square there. On the inside, I have the square root of this thing. So that's all I'm integrating. It can get a little messy, but sometimes it works out so pretty. So we have 1/2 x cubed over 3 minus 1 over x from 1 to 2. When you plug in those values, leaving the 1/2 on the outside, I get 8 over 3 minus 1/2 minus, plug in the 1, and I'm going to end up with, we have 8/3 minus 1/3 minus a half plus 1. So we're going to end up with 14 minus 3 plus 6. all over the common denominator. On the top, we're going to get 17. On the bottom, we get 12, and that's the arc length. Next example, y equals 2x to the 3 halves plus 3. On the curve, on the interval 0 to 9. Okay, longer curve here. So y prime is going to be 3x to the half plus 0. Y prime squared is 9x. So I'm integrating from 0 to 9 the square root of 1 plus 9x dx. So u substitution, u is the stuff under the radical. Take the derivative. All I'm missing is the 9. So what I'm integrating is 1 plus 9x to the half. I've got a dx. I'm missing a 9, so I multiply by 9 and I divide by 9. So this is going to be, let me write this out here. This is u to the half, and this is du. So it's a simple power rule integral. We've got the 1/9 on the outside. I'm going to add 1 to the power and divide by 3 halves. Notice that when you divide by a fraction, the denominator flips up and multiplies the numerator. Evaluated from 0 to 9. So I have 2 over 27, and this is the square root of 1 plus 9x, and then cubed, evaluated from 0 to 9. So this one is not going to be pretty. 227. Plug in the 9. I'm going to get 1 plus 81. So it's 82, but that's cubed. Minus. Plugging in the 0 for the x. This is a 0. I get the square root of 1 cubed. It's just a 1. And that is exact. So you can leave it like this if you want. Or you can stick it in your calculator and you're going to get something like 54.9 something. Good enough. And remember, this is exact. Before, we took a piece of a curve or many pieces of curve, and we had a given area, and we rotated that area about an axis, and we got a solid. Now we're going to take just the curve instead of all the area, rotate that curve about an axis of rotation, and it's going to give us a surface. And we can find the area of that surface by doing what we did with arc length, but now we're going to take an element there, and we're only looking at the very tip of that element, right? The arc length at the top. But we need to know the radius because we are creating this, this three-dimensional surface, and we need to find the area. But if we split it into an infinite number of elements like this, then we can find just the area of that little arc length as it rotates about the axis, and then we can find the surface area of just that band. Now when we take that band, I'm going to make it a little bit bigger here, and we rotate that one piece of arc about an axis of rotation, then we're going to end up with something that's equal to a strip, a slice of a cone. And we we have a formula for the area, surface area of a cone, and this is going to be a little sliver of that. 2 pi r, that's the circumference of the circle, where we're finding, here's my axis of rotation, r will be that distance right there, and we're multiplying that by L, where L is the arc length that we found on the previous page. Okay, notice in this problem that your radius is the distance from the axis of rotation to the function, right? It's this distance right here. So for this problem, when we find our surface area, we have 2 pi, the integral of r, which will be the function minus the axis of rotation, which is 0, times the arc length portion. This is squared dx. Okay? Now, what if we took the same thing, and by the way, if you were doing it, you could have a function with respect to y and do the same thing here. By the way, my limits are from a to b for this problem. Okay, now what if we took that same type of thing and rotated about the y-axis? Let's do that on the next page. Okay, taking that same piece of curve and rotating it about the y-axis, we get this sort of funnel-looking thing. In this situation, if this function is given as f of x, and it goes from a to b, but we're rotating it about the y-axis, then the radius for this problem, the distance from the axis of rotation to the curve, but we're doing it with respect to x, that means that our radius is whatever the x value is. And notice that x only goes from a to b. There's a hole in the middle, right? It's got a hole. Your limits will dictate where your surface is. So using x as the radius, because we're going about that y-axis, and we have a function with respect to x, then the limits will take care of cutting that hole out. Integrating from a to b, the radius is x, and we have the arc length portion, function prime squared under the radical, and a dx on the outside. Now let's work some problems. Okay, we're going to take the curve 9 minus x squared, that's an upside down parabola, on the interval from 0 to 3. So plug in a 0 and I get a 9, plug in a 3, I get a 0. So we have this piece of curve, and we're going to rotate that curve about the y-axis. So you see when we rotate this curve about the y-axis here, we're going to get this kind of a dome looking thing where the radius is just the x value, right? And we have to find the arc length portion by taking the derivative, square the derivative, and we're ready to plug all this stuff in. Our surface area is 2 pi, integral from 0 to 3. The radius is x, and the arc length portion is 1 plus 4x squared under the radical dx. This is just a quick, easy substitution integral. Let me rewrite it. Here's my cheater box right there. let me rewrite this as the integral of 1 plus 4x squared to the half power, and the rest of the problem is x dx. But you see, if the inside is u, and we take the derivative of u, we get 8x dx. So in my problem, I have u to the 1/2, and I need the du, so I'm missing the 8. And I multiply by 8 and divide by 8. I haven't changed the value of anything. So we end up with surface area equals pi over 4. I've got u to the 1/2, so I'm going to say 1 plus 4x squared, add 1 to the 1/2, divide by the new power, evaluated from 0 to 3. Let's make this a little bit neater. The 2 in the denominator is going to flip up to the numerator up here. That's going to cancel and leave me with a 2 here. 2 times 3 is going to give me a 6. So on the outside I have pi over 6, and then I just have 1 plus 4x squared to the 3/2 power from 0 to 3. So let's do this. Pi over 6 on the outside. When I plug in the 3, I'm going to get 4 times 9 is 36, plus 1 is 37, so to the 3/2 power, minus, plugging in the 0 right here, I get a 1. Again, this is ugly, but it is exact. And if you stick it in your calculator, $117.3 something, 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 something. Okay, let's try this one. It's the same function, but now we've got the square root of it on a little bit of a different interval, and we're rotating it about the x-axis. So if we're rotating about the x-axis, then the radius is going to be the curve itself. So this one can be a little bit complicated with the algebra. We have y prime is going to be, remember, this is blob to the half. So we're going to get 1/2 blob to the minus 1/2 times the derivative of the blob. Make it pretty. The 2's cancel. I'm going to get x on the top, a minus sign, and a square root in the denominator. And that's y prime. Y prime squared is going to be positive x squared over squaring that square root. We get 9 minus x squared in the denominator. Now we're going about the x-axis, so the curve itself is going to be the radius. And we're going to get 2 pi from 0 to 2. The radius is the curve. And we're going to have, let's do the square root of 1 plus this down here in our cheater box. So the common denominator underneath the radical, 9 minus x squared plus x squared. This is going to give me 3 over the square root of 9 minus x squared. That's the entire arc length portion. Look what happens. Isn't that pretty? dx. And we are just integrating 3 dx. So that's 6 pi x from 0 to 2. I get 12 pi. Booyah. Okay, some of these you're going to go, obviously, through some algebraic gymnastics to get to where you have a very simple integral. In some of these, you'll be told in the homework, just set up the integral because you won't be able to solve it at this point. So take your time, be careful with the algebra, and let me know if you have any questions.